An ideal monatomic gas is kept in a container, volume and a pressure. 310 kelvins of pressure or whatever. State what is meant by an ideal gas. What is meant by? What are the limitations of an ideal gas? Yeah. They'll ask this occasionally, right? It's like, what is meant by an ideal gas, right? Ideal gases, by the way, what they collide elastically. They don't stick to each other, right? So the behavior of a gas deviates from the ideal gas law when you've got like phase changes happening, like for example, water gas, the steam, right? The gas phase starts to like become water, right? They also one other thing about an ideal gas is that the particles themselves take up no space in an ideal gas, and anyway, we only need one mark, so just state something that's true about an ideal gas. So in an ideal gas, literally you have these geometric points. They collide elastically. They don't exert forces on each other other than to like repel each other. They don't stick together, in other words. There's no van der Waals forces. Okay. Calculate the number of atoms. Use the ideal gas law to find, right? Don't they tell you? They tell you the pressure. They tell you the kelvins. We know R. We can look that up. They tell us the volume. So you can figure out N, right? And then N, the number of molecules, is just going to be N times Avogadro's number. Okay. Let's see. Calculate in joules the internal energy of the gas. It's like, okay. It's like, well, what if we didn't study this? So we're going to do, from our perspective, right? We're going to go kinetic energy is 3/2 R over Na times T, right? Okay. That's the energy of one particle, right? So if we take that and multiply it by, the number of particles, right, then you'll have the total energy, right? And the number of particles is, of course, M times Na, right? So, I mean, you can feel free to multiply by Avogadro's number and then later divide by it, but you can also just go boom. Wouldn't it just be 3/2 nRT? And that, again, that formula is in the data packet at the end in the options for thermodynamics. But we can use our Boltzmann's equation to do that. Okay. The volume of the gas is increased to 6.8 times 10 to the minus fourth at a constant temperature, right? It's like, ooh. Which, by the way, if it's expanding, you would actually tend to cool down. Expansion cooled it down. So if you did it quickly and heat couldn't flow in, it would actually cool down a little bit, right? Okay. But they're saying, well, it stays at a constant temperature. So they must do it slowly, or we wait until it gets back to the temperature. So calculating Pascal's the new pressure of the gas. There's two ways to do this. We have a different volume, right? And we now know the number of moles, right? You figured it out there. So you could just Puvnert it. Probably most folks would just do that. But I feel like that's working too hard. Can't you just take the original pressure and multiply by the ratio of the volumes, right? Like I'm pretty sure the volume is going to, or the pressure is going to decrease. So if you multiply by the ratio is 2.1 to 6.8, right? Anyway, just saying. Save yourself some time, right? So the initial pressure would be this, right? This ratio of volumes tends to decrease the pressure because we're increasing the volume. And so you'd set up the ratio this way. And this is what I meant by the George Penck challenge. Okay, you just wing it, baby. Don't, the formulas are for, I don't know. Formulas are for other people. Okay, let's see. Explain in terms of molecular motion this change in pressure. Okay, now be careful. Remember, it's a constant temperature, so these molecules aren't going slower. They might look like they do in a simulation. They're not going slower. On average, they've got the same speed, right? That's not what's going on, right? So why is there a change in pressure? Keep in mind that in this thing, right, it's like we had a piston, and the piston was here, and we moved it to here. It's like, right? Don't they have more space? So doesn't it take longer? If they're going the same speed, it takes them more time to travel from one side to the other. Imagine one that's just ponging back and forth, boom, 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 boom. It's going to, take longer to go across the space. Therefore, it'll hit the walls less frequently. Remember that force is caused by the aggregate change in momentum over time, right? And pressure is force over area. I don't know how much you have to say. It's 2 marks, right? But okay. So because it's a bigger container, it takes longer to go back and forth. So therefore, it strikes the walls less frequently, or the time it takes to strike the walls is a bigger time. So therefore, the force is smaller. And since pressure is force over area, is there room to say all that? I'm always curious. Seriously, if you're going to prove this analytically, you'd have to say so much. Could you fit it all in there? I don't know. See what you can do. I think I wrote a thesis here, and 2 of the things were actually on the mark scheme. But I sort of felt I don't know. Yeah. Anyway, good luck.